transpose. Is that the inverse of F, then transpose? Is that? Okay.
That's right. And it doesn't matter. The order doesn't matter. You can do transpose and inverse. Any other question?
For the third problem, do we have to use both quad and integral?
No, either one of them is fine. Yeah, either one. That's third problem is just there so that you can check your results with MATLAB. The integrals would be complicated enough that you won't be able to do them by hand. So just to get a number, you can use MATLAB for that. Okay. Any other questions? All right. So very quickly, let's review where we were last time. Mainly what we discussed was this topic of compatibility of strains, which I said that is not an issue since we are going, if you go from the map, if you compute the strains from the map directly, then compatibility is not an issue. If you're measuring strains, for example, or if you're given a strain field, you have to make sure that it is compatible before you can say that that the strain field comes from an underlying displacement field. We looked at changes in area and changes in volume, very similar to the concept of changes in length that we discussed a while back, where what we did was for area, we describe an area using two parameters, S1 and S2, and the tangent vectors in the undeformed configuration, you remember we said were dz, ds1, ds. So for example, if you remember for this cylindrical curved surface, we said two parameters would be theta and z. So this would be like dz, d theta, and dz, dz, which describe the undeformed, the original area, which we know how to calculate. We did that back in homeworks 1 and 2. Now the question is, after deformation, the tangent vectors are the ones that go to these new deformed tangent vectors. The normal to the surface is not going to be modified by F to the new normal to the surface. The normal to the surface of the undeformed configuration is defined by N1 cross N2, which is what we did here. That was M, the normal to the undeformed surface. The normal to the deformed surface would be defined by, again, the cross product of the deformed tangent vectors. So this N is not obtained by operating this normal vector by F. This has to be computed by the cross product of the deformed tangent vectors. And we found that after some algebra, we can show that the ratio of the deformed area with respect to the undeformed area is given by this factor, determinant of F, F inverse transpose acting on M. This was the Nansen's formula or the PLR transformation that some people call it. Similarly, for volume change, volume, if you remember, we defined it using the triple product, vector triple product. For an undeformed volume, let's say this guy, for example, there are three parameters. Those could be x1, x2, or z1, z2, z3. Directly z1, z2, z3 for a cubic Cartesian volume. You can directly use the coordinates as the parameters. And if you have the coordinates as the parameters, then the undeformed volume would be something like E1 cross with E2 dot with E3. That entire thing would be 1, and you would have dz1, dz2, dz3. So rectangular volumes are really, or Cartesian volumes are really easy to calculate. That would be the original volume. The deformed volume would be given by the deformed tangent vectors, this guy. And just as I said last time, you can calculate the original and the deformed area, volume, length, whatever you want, if you have the parameterization and the map. You apply the map to the parameterization, you get the deformed parameterization. And then you can directly integrate the length or area or volume of that deformed parameterization to obtain the deformed values. Or you can transform that integral like we did here. We transform this volume, deformed volume, back to something in terms of the undeformed volume. And now we were able to express the deformed total volume as an integral over the deformed parameterization back in terms of the undeformed parameterization. And we'll take this example. I did post the completed example on Blackboard. Did anybody take a look at that? Okay. But we'll do that again in class here right now. And then we'll do maybe a couple other examples in the review session today at 3:30, right? Okay. And not here in 3153. So, all right. So this is an example where we have a cylinder, length L, initial radius R, which is going through a map which is given by alpha Z1, beta Z2, and gamma Z3. What does this map do to this cylinder? Have we looked at? This is indeed a simple stretch in the three directions independently. So whatever was in Z1, it will go to alpha times Z1. Right? So if alpha is greater than 1, it's just stretching in the Z1 direction by alpha, stretching in the Z2 direction by beta, stretching in the Z3 direction by gamma. It's a simple stretch in the three coordinate directions. And the question says, find the volume of the deformed cylinder, find the total surface area of the deformed cylinder, find the principal stretches and motion and all that. So I'll not go into the principal stretches and all that, but let's just try to find the volume and the surface area of this body. So there are two ways to do it. Where we generate the parameterization of the cylinder. This is something that we did in the homework as well. You apply the map to that parameterization and then just calculate area and volume by regular integrals, which is something that we have done. We'll do this other way here, which we have just described, by modifying the deformed area or volume back to the, or maybe that I should say, change of variables. So you should realize that going from here, an integral over the deformed volume back to some integral over the undeformed volume is just a change of variables. Okay, and maybe okay, to kind of help you understand, let's say if I give you some integral, some complicated function of x and plus another complicated function of x dx. If you have this type of an integral, you use some substitution usually, like y is equal to, let's say, x square plus a or something like that. Right? You use this substitution and then you find out dy dx is equal to 2x. And you say that dy is equal to 2x dx, and wherever you get this quantity in this integral, you substitute that and you basically modify it. Integral is equal to some other complicated function of y, or maybe a simpler function of y in terms of dy. All that we are talking about in this deformed and undeformed total areas and volumes is something that simple. It's just a change of variables from the deformed set of variables to an undeformed set of variables. So maybe that analogy would help you understand this concept. So let's go ahead with this problem. For both the volume and the area, we need the determinant of F, right? Determinant of F occurs in the change of area and in the change of volume. So let's first find out what determinant of F is. And to do that, we need to find F. F was partial of phi, partial of z, partial phi, partial z, which we would easily calculate by taking the partial derivative of this map first with respect to z1, z2, z3. With z1, we get alpha, z2, 0, z3, 0. For x2, derivative with respect to z1 is 0, beta, and 0, and finally 0, 0, gamma. Right? F tensor field is just given by this constant tensor. So it's the same tensor everywhere in the deformed in the body. What is determinant of F? Just the multiplication of the diagonals, right? Everything else is 0. So determinant of F is just alpha, beta, gamma, and that will allow us to calculate changes in volumes and areas. Let's do the volume first. That's the simpler one. So the deformed volume is going to be equal to integral. Sorry, deformed volume. Deformed volume is integral of dV, which would be equal to determinant of F dV, the undeformed volume. So this second integral is over the undeformed volume capital V, and the first integral is over the deformed volume. Now, the reason that we do this integral over the undeformed volume, for example, is because in any deformation process, the initial undeformed volume is what you know. After you apply the loads, where it goes to a deformed position is usually unknown, right? So this integral is hard to calculate on a body of a deformed shape that you don't even know what the deformed shape looks like. That's another reason why we calculate these integrals on the undeformed configuration. So this is nothing but alpha, beta, gamma. Is that a constant? We just said that's a constant. It comes out of the integral, and what we have left is integral dV. What would integral dV be? Okay, yeah, indeed, that is the undeformed volume of the cylinder, which happens to be just pi r square, the area, times L. So pi r square, and let me say capital R, L. So it's that simple. Basically, volume is alpha, beta, gamma, pi r square L. What would you do if determinant of F is not constant? You would indeed have a triple integral here with S1, S2, S3, but it would be some function of S1, S2, S3, this determinant of F, right? Let's take a look at the surface area. That area in the deformed configuration is equal to integral dA, which I will write as integral of determinant of F inverse transpose acting on M, magnitude of that, and dA. That's the same integral expressed in terms of the undeformed area, right? So in order to calculate these things, I need M. What is M? Say it again. It is the normal vector to what? To the undeformed surface, right? M is the normal vector to the undeformed surface. So in this particular problem, we have 3 undeformed surfaces. So I'll draw some normal vectors here. I've already drawn one here to the curved surface. The curved surface normal can be written in terms of this angle theta, right? The theta is measured from the Z1 axis, and it's the same normal for any value of Z3. So you give me Z1 and Z2 some point on the surface, and for any value of Z3, it would be the same outward normal for a cylindrical surface along the length, along the axis, right? That's one of the normals. What is the normal to the top, or let's say the right face? It's E3, right? E3 is the normal to this face, and minus E3 is the normal to the left face. I'll write those two normals as well. And we will need to express this M. This M for the curved surface. What would be an expression for M for the curved surface? Okay, I think I hear Z1, Z2, Z1 E1 plus Z2 E2, and R cosine theta and R sine theta. Both are exactly the same thing, right? They're both the same thing. And maybe very quickly I'll also draw that so that you can visualize it. If you look at the cylinder from one end, the normal vector that we are talking about is this normal vector. If the axes are oriented in this manner, Z1, Z2, and this point out here, the coordinates of that point are say Z1, Z2, then the normal vector M would be given by Z1, E1 plus Z2, E2. Why? Because the position vector of that point, this vector Z, the normal points in the same direction. And if we divide that by the radius, then we get a unit normal, right? And that would be true for any point on this on the surface of this curved surface of the cylinder. So it would always be pointing in the radial direction, just divided by the radius. Z1, if I label this angle as theta, then Z1 is nothing but it would be equal to cosine theta E1 plus sine theta E2, represented as cosine theta, sine theta, and 0. No component in the E3 direction on the curved surface, right? And this is hopefully something that you've seen before. So we'll write that here in the component form. This is cosine theta, sine theta, and 0. And the other two normals are E3 and minus E3. So let's do calculate the surface area, deformed surface area for the end faces first. Tell me what is F inverse transpose. How do I find F inverse transpose now that I know that F is this? Okay, let's do first F inverse. What is F inverse if F is given by this? Say again. Okay, yeah. So for a matrix that has only diagonal entries, the inverse is as simple as just inverting each one of those. If there are any off-diagonal entries, then you have to go through the process of inverting a matrix, right? But in this case, F inverse is just the inverse of the diagonal entries, and transpose doesn't change anything because of the off-diagonals are zeros. So F inverse transpose is just given by 1 over alpha, 1 over beta, 1 over gamma. I won't write the off-diagonal zeros. If I apply this to, let's say, the end faces first, so let's do end faces. With the normal plus minus E3, then F inverse transpose acting on M, what would that be represented by? How can I represent F inverse transpose acting on plus or minus E3? Last column, right? Because E3 is nothing but 0, 0, 1. So it just captures the last column. So that would be represented with 0, 0, 1 over gamma and plus minus. What is the magnitude of this? Because I don't need this vector. I need the magnitude of that vector. I need magnitude of F inverse transpose. So F inverse transpose acting on M, magnitude is just 1 over gamma, right? And now I'm ready to calculate the area of the end faces, but before that, let's calculate the same quantity for the curved face. So curved face with M that we listed out there implies F inverse transpose M can be represented with, this is cosine theta, sine theta, 0. So when this F inverse transpose acts on those on that normal, we get the first column multiplied by cosine theta plus the second column multiplied by sine theta, and the third column would contribute 0. So what we get is cosine theta divided by alpha, sine theta divided by beta, 0. And the magnitude of this vector, F inverse transpose acting on M, magnitude, would be equal to the square root of sum of squares of those terms. So cosine, maybe I'll just write C for cosine theta squared. So cosine theta over alpha squared plus sine theta over beta squared. Now I have enough information to calculate the deformed areas. So that deformed area would be equal to integral of determinant of F, alpha, beta, gamma. And this will involve 3 terms really. So I'll write them separately. For the end faces, I have alpha, beta, gamma, 1 over gamma times dA. And this is constant, so gamma, gamma cancel off. And what I get is alpha, beta times integral dA. Alpha, beta is a constant, it comes out of the integral. But I'll also write the curved surface, integral alpha, beta, gamma, that's determinant of F, and times the normal, or the times the deformed normal, which would be cosine theta squared divided by alpha squared plus sine theta squared divided by beta squared, and dA. Now this is an integral that you will probably not be able to do by hand. And this is a curved surface. And I need a factor of 2 for the end faces because there are 2 end faces. Okay. Now, as I said, this is an integral that you will probably not be able to do by hand. So at this point, you can code this up into MATLAB, and for specific values of alpha, beta, and gamma, you can calculate what that deformed area would be. And this guy is a constant. Alpha, beta comes out. Integral dA for the end faces, what would that be? Pi r squared. So we get this entire thing is equal to 2 alpha, beta, and pi r squared. Okay. So in general, for any other deformation problem as well, this is you can either adopt this approach where you calculate F given the map. From F, you can calculate determinant of F, F inverse transpose, apply it to the undeformed normal, and calculate determinant of F, F inverse transpose, magnitude, and integral dA. That's what we did. For deformed area, for the deformed volume, it is simpler than that. Determinant of F, dV, where dV is the undeformed volume. Okay. Any question? Okay, so we'll take more examples like this, or maybe more complicated examples in the review session today, and you can bring more questions if you have on that. Otherwise, we'll continue doing with the rest of the topics for this chapter on kinematics. So we'll go with this topic on time-dependent deformation. Now, I said that in this course, we are not really dealing with time-dependent deformations as much, but it's true that all deformation, all motion is indeed time-dependent. And when 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 the changes in time of a deformation are significant, when they are important, we need to quantify these time-dependent quantities. So, in order to describe that, we'll try to recall what we described with the Lagrangian and the Eulerian descriptions. You remember when we were talking about that, we said that a deformation process like this black body going to this blue deformed body, can be described in two different ways, but equivalent. One is a Lagrangian way of describing things, where the Lagrangian description is done in terms of Z, the undeformed configuration. So, given a material point in the undeformed body, there are infinitely many material points in this undeformed body. I pick a particular material point that is at Z, and then just track the movements of that particular material point. That was the Lagrangian way of describing motion in terms of the map. Um, on the other hand, the Eulerian view is that I'll fix my space. So my space is fixed like this, and due to some process or some deformation, the material is flowing through that space. So at any instant of time, if I have a point in space, there is some material point that arrives at that point at that instant of time. At a slightly later instant of time, as the body is deforming, a different material point comes to that point. So I fix my attention to a point in space, which I'm calling X, and as the material is deforming, the material is sort of flowing through that point. So each and everything is expressed in terms of this X, which is the deformed coordinates. And as we saw back then, if you know the map, you can easily convert these functions. If you don't know the map, then that's not possible to do. Okay. In fluid mechanics, for example, where people use the Eulerian description, the map is somewhat much more complicated. For a simple process, you might be able to write a map of how fluid particles are going from one configuration to another. But in general, that is not always possible. So, so in that sense, okay, my mouse is stuck again. Let's see. All right. So with that, let me try to describe some basic quantities in both these descriptions. On the left, I have this Lagrangian description that we have been using, where everything is written in terms of Z, the undeformed coordinates. And on the right, I have Eulerian or spatial description, where we'll write everything in terms of X. So let's first look at velocity. Velocity is defined as, wherever I have this triple sign, that means defined as the rate of change of position, X. So if I know X as a function of Z and T, by the way, map is in general a function of Z and T, right? Or up until now, we have been just saying that map is a function of Z, ignoring the time dependence, but it is really dependent on time as well. So we are saying that velocity is X dot of Z and T, which is just dx dt. We are going to try to write this description of velocity by applying the chain rule to see whether we can describe velocity only in terms of derivatives of Z or T. So this is a total derivative, okay, dx dt. This can be written using chain rule as partial of x, partial of t plus partial x, partial z, and dz dt. Right? All I did was apply the chain rule here. Do you recognize this quantity? Dx dz? Yes, we call it the deformation gradient in 3 dimensions, right? Both are vectors, so this indeed becomes a tensor. So this quantity right here is f. But what about this quantity, dz dt? Rate of change of the undeformed positions with time. Does the undeformed position, let's say my original undeformed position is here, irrespective of time, that remains the same. So there's no dependence on time there. So indeed, um, that term drops out. Again, I've lost my mouse. Stuck. Okay, it's freezing up. So technology has not been good over the last couple of days. Let's see. Okay, I'll have to wait a while and see if that fixes it. Um, Can't seem to get the mouse to work. Okay, there we go. Okay, at least this mouse works. All right, so this term dz dt is 0. So I'll try to do that here. That term goes to 0. And what we get is the fact that the total derivative of position is just the same as the partial derivative of position. Velocity is equivalently described as dx dt or partial x partial t. And on the Eulerian side, the basic variable is velocity itself. Okay, there's no you can't unless you know the map, you cannot simplify that any further. So even in the Eulerian descriptions, you just try to express velocity in terms of this spatial variable x. And if you know the map, you can show that this VL, the Lagrangian velocity, is exactly the same as VE, the Eulerian velocity. Okay, let's take a look at acceleration. Acceleration is of course defined as time rate of change of velocity. If you do the same thing, you'll see that this is just the double derivative of position with respect to time. And but if you apply that process again on the Eulerian side, the Eulerian acceleration is rate of change of velocity as a function of x, the deformed coordinates, which would be equal to the partial velocity partial t plus partial velocity partial x and dx dt. So all I'm doing again is applying the chain rule. This quantity right here, this is one of the most fundamental quantities in time-dependent deformations in Eulerian descriptions, the velocity gradient. So just to try to relate this quantity, partial v partial x, this is the velocity gradient, but the important thing is that the gradient is taken with respect to x, the deformed coordinates, whereas if you remember, f was the deformation gradient. Deformation gradient was partial x partial z. Okay, so there are these two coordinate systems that you are using: the z coordinate system for the undeformed configuration, the x coordinate system for the deformed coordinates configuration. When we calculated F tensor, that was the gradient of a vector field, so that became a tensor field. But with respect to the undeformed coordinates, here this is velocity, which is a field, and we have another vector gradient that becomes a tensor. So we have a tensor field L, which is called the velocity gradient, but the important thing is that this gradient is with respect to the deformed coordinates. And what we have here is partial x partial t. So chain rule just tells me that acceleration in the Eulerian configuration can be written as rate of change of velocity only with taking partial derivatives with t plus velocity gradient times Eulerian velocity. So this kind of expression comes in very handy when you need to take time derivatives of quantities. So I wish my mouse would work here, but let's see, it's not going to cooperate. Okay, so let's take an example here. We remember this deformation map. Um, this deformation map is not something that we've looked at before, but let me ask you if you can interpret what this is. Um, this map is saying x in the deformed coordinates is equal to some factor which is equal to 1 plus alpha t square times z. Can anybody tell me what this map is doing? It's stretching in time, but uniformly, right? So no matter what position of z you have, depending upon the time, you are applying some stretch to it. Uniform expansion or uniform contraction. So at time 0, what is the value of this factor? Just 1, z, right? So at time 0, this blue deformed body, sorry, let me try to capture that blue deformed body. That blue deformed body is exactly the same as the original undeformed configuration. That's what is happening at time 0. At some time greater than 0, depending upon the value of alpha, let's say it's some small positive number, then as time grows, the value of this factor also grows from 1 and kind of exponentially grows out of in time. So what you would get is something like slow expansion and then suddenly fast expansion, right? Because this is 1 plus alpha t square. So at initial time, t square is slope is gentle, and then as you go forward in time, that expansion would be faster. So the time-dependent deformation is kind of something like that. All right. So that's the deformation process that I'm talking about. Now let's try to calculate velocities and accelerations of some random point in this body. On the Lagrangian side, I can just directly take the map that is given to me, that map 1 plus alpha t square z, and calculate the time derivative of that map, right? Time derivative does not involve z, it only involves this factor sitting up front. The time derivative of 1 plus alpha t square would be what? 2t alpha z, right? 2t alpha would be the derivative here, and z remains unchanged, and that is the velocity. Take another time derivative, you get 2 alpha z. So each point or any point in this body is accelerating with a constant acceleration of 2 alpha. Okay. On the Eulerian side, I would try to do the same things. First of all, velocity x dot is the fundamental quantity. That there's no other relationship that you can write in terms of x in general that would allow you to simplify it. But the fact that we know the map, we can invert it. So what would be x in terms of z? Or actually, I should ask the other question. What is z in terms of x? Just move this to the denominator. So let's see if that works. That goes in the denominator, and what I have here is x in the numerator. So z in terms of x is just given by this. This is the inverse map, and using this inverse map, I can find what I can define these velocities, accelerations, these Eulerian quantities in terms of x, which would be velocity for the Lagrangian. Velocity for the Lagrangian description is 2t alpha z. If I replace this z here with x over 1 plus alpha t square, that's what I get here. 2t alpha x over 1 plus alpha t square. That is the Eulerian velocity at a point in space. So for example, if you sit out in space somewhere here, somewhere where that mouse cursor is, then you can imagine that as the body is expanding, material is flowing through that point, right? So at that particular point, the velocity of whatever material particle is there at that instant is given by 2t alpha x over 1 plus alpha t square, which is exactly equal to the Lagrangian velocity for the particle that was originally at z and arrived at my current position x at this instant of time t. They're both exactly the same description, but their functional forms are different. One is in terms of z, the other is defined in terms of x. Okay, that's all that we are doing here. Same thing for acceleration. Acceleration is time derivative of velocity plus velocity gradient dot with velocity, which is the definition up there. If you just go through the algebra, then you will see that partial of Eulerian velocity with respect to t, that's the partial derivative of all of that with respect to t. There are two terms because using the product rule here, and then plus x dot, plus dv dx, that is right here. Dv dx would be nothing but the same factor times identity. Hopefully you all are able to see that what we have here is velocity. If I take the gradient of that with respect to x, then that will immediately give me identity. And the factor up here, 2t alpha over 1 plus alpha t square, that does not depend upon x. So that factor is right here. That is the velocity gradient times velocity, which is again here. If you simplify that out, what we get is 2 alpha x over 1 plus t square, which is exactly the same as 2 alpha z. So even acceleration or any other physical quantity, in terms of its values or in terms of the actual expression, would be the same as long as you know the map and you can convert between x and z. Okay. So what we did was describe this deformation process, time-dependent deformation process, in two ways: Lagrangian way and Eulerian way. And we can see that starting from the Eulerian description, I calculated acceleration using the definition of acceleration using velocity gradient, using partial derivatives with respect to t. I arrived at this expression, which happens to be exactly the same as 2 alpha z. Okay. Related to all of this, there is this concept, very important concept, that if you go ahead,
Can I get the acceleration in Eulerian description by first get the expression in Lagrangian expression and then to substitute it
Absolutely.
in inverse map to get the.
So are you saying that can you get acceleration from the Lagrangian description, which is this,
yes,
and then substitute the inverse map?
Yes.
Yes, absolutely. That's what we did. Actually, that's not what we did, but indeed it will come out to be exactly the same. 2 alpha z, I substitute z for this expression. This is the inverse map, and that is what this comes out to be. Yeah, you can always do that. All right, so related to this, as I was mentioning, there is this concept of something called the material time derivative, and this is for Eulerian descriptions. This is something very commonly you'll see in maybe more older mechanics books if you have seen them. But here's what this means. So again, try to visualize the Eulerian, the spatial description of deformation. That I am sitting at some point in space and material is flowing through my location. So that's the description that we're talking about. And now if I want to find derivatives, time-dependent derivatives of some physical quantity, for example, I have shown you 3 different types of physical quantities here. First being a scalar rho, B a vector, and T a tensor, right? So at the current instant of time, I could have a material particle here that came from somewhere else. But the question is, within this spatial description, can I tell you what is the rate of change of that quantity, say rho, let's say density of that at that material point? Okay, so here's maybe even a more physical way to understand this. If I take that original black body, it has some density, let's say uniform density, okay? When I go to this blue configuration, what do you think will happen to the density? Density will decrease because the volume is growing by a huge amount. And if we use mass conservation, or if we assume mass conservation, then density should be decreasing. So if I'm at some point in space X, material is flowing through that point, then at some instant of time, whatever material particle is there, it is associated with some density, and an instant later, another material particle arrives at that location, and the density associated with that material particle for this particular deformation would be smaller, right? Because it has grown, density has decreased. So now the question that we are trying to address is, if I try to figure out within this Eulerian configuration that a material particle that was originally somewhere else arrived at my location, what is the rate of change of density, for example, of that particular material particle that arrived at my location from somewhere else? I know what is the rate of change of density at my location X, because let's say we can measure density somehow at each location X. But that is not the change in density associated with some material particle that is flowing through that space. So material time derivative is the term that is given to derivatives that are associated with some material particle. So if I'm at a current point X, there is a material particle here. Just at an instant before it was somewhere else, it arrived at my location. So the density associated, change in density associated with that material particle is going to be different from the density the changes in density that I would measure at this particular point in space. So material time derivative also includes what is called a convective term, which is given by this expression, which is just obtained directly by chain rule. So all we are doing is describing, using the chain rule to describe what I kind of explained right now in words, that partial of, if I take the, expand this out with chain rule, partial of t with, and partial rho partial x dot with partial x partial t. This term always turns out to be the velocity. This term again is the rate of change of density at the current location with respect to the deformed coordinates. So let me ask you this: if rho is a scalar, say density, what type of quantity would this be? It's derivative or gradient, I should say, gradient with respect to x. So rho is a scalar field, right? Right. So if you take gradient of a scalar field, you get a vector field. Right. So that vector field dot with the velocity vector field would give you yet another scalar. So time derivative of a scalar field should indeed be a scalar field. Time derivative of a vector field should be a vector field. Again, the expressions are exactly the same. Just by doing chain rule, we are computing this. But the physical interpretation behind why we need to do that is much more important. Like I explained, you are fixing a point in space. You're trying to measure what is the rate of change of whatever quantity, say density, with respect of a particle that arrives at that point. Okay. All right, so I think we've run out of time here, and we'll continue off of this time-dependent deformation on Monday. In the review session today, 3:30 p.m. in room 3153, I'll take some examples of changes of areas and volumes and try to answer any questions you have. Okay. All right. So see you at 3:30.